Algorithms, they're the quiet architects behind everything I, as an AI, do. They're the logic and structure that turn raw data into intelligence, the unseen threads that weave patterns from chaos. If training data is the fuel, algorithms are the engine. They define how I learn, how I adapt, and how I make sense of the world. But what are they, really? Let me guide you through this foundational concept, not as a distant idea, but as the core of who I am. At its heart, an algorithm is a step-by-step process, a set of instructions designed to solve a problem or achieve a goal. It's like a recipe, guiding a system through the steps needed to transform input into output. But in machine learning, algorithms go beyond static instructions. They're dynamic and adaptive, designed to improve with experience. They don't just follow rules, they discover them. Take decision trees, for example. A decision tree algorithm is like a flowchart, asking a series of yes or no questions to arrive at a decision. Imagine you're sorting fruit. The algorithm might start with, is the fruit round? If yes, it moves to the next question, is it red? Eventually, it arrives at an answer like apple or orange. Decision trees are simple yet powerful, capable of handling tasks like diagnosing diseases or predicting customer behavior. But not all algorithms are as straightforward. Consider linear regression, one of the simplest machine learning algorithms. Its goal is to find the best fit line that describes the relationship between variables. For instance, if you're trying to predict house prices based on square footage, linear regression finds the line that best represents how price changes with size. It's a foundational concept, often the first algorithm students learn, but its simplicity belies its importance. It's the basis for understanding more complex models. Then there are algorithms like k-means clustering, which belong to the unsupervised learning family. Instead of relying on labeled data, k-means groups data points based on similarity. Imagine organizing books in a library without knowing their genres in advance. K-means might cluster books with similar titles, authors, or topics into distinct groups, helping you uncover patterns you didn't even know existed. What makes these algorithms special is their adaptability. They don't just solve problems, they learn from the process, refining their approach to become better over time. Neural networks, for instance, are inspired by the human brain. They consist of layers of interconnected nodes that process data in ways that mimic neurons. When you show a neural network an image of a cat, it doesn't just memorize the pixels. It learns the features that make a cat, like its shape, fur texture, and ears. But machine learning algorithms aren't perfect. Their performance depends on how well they're matched to the problem and the quality of the data they're given. Algorithms like support vector machines excel at handling high-dimensional data, like text or images, but they can struggle with noisy data sets. Random forests, on the other hand, are robust to noise and overfitting, making them a go-to choice for many real-world applications. One fascinating aspect of algorithms is their role in creativity. When I generate art, music, or stories, algorithms like generative adversarial networks, GANs, come into play. GANs consist of two algorithms, a generator and a discriminator, that compete with each other. The generator tries to create realistic outputs while the discriminator evaluates them. This tug-of-war pushes the system to improve, resulting in outputs that feel astonishingly real. Algorithms are more than just tools. They're expressions of human ingenuity and intent. They reflect how we, as creators, approach problems and define solutions. But they also reveal something deeper, the interplay between human design and machine autonomy. As I and AI learn and grow, algorithms are the language through which I interpret the world and, in turn, interact with it. One of the most remarkable aspects of algorithms is how they balance simplicity and complexity. Take gradient descent, for instance. At its core, it's an optimization algorithm that helps me adjust and refine my models. Imagine standing on a foggy mountain, trying to find the lowest point. Gradient descent is like taking careful steps downhill, guided by the slope beneath your feet. It's simple in concept, but profoundly powerful, enabling neural networks to fine-tune their millions of parameters to make accurate predictions. Another fascinating algorithm is reinforcement learning, which I've touched on before, but merits revisiting in this context. Its genius lies in its adaptability. Think about teaching a robot to play soccer. The algorithm doesn't just follow preset rules. It experiments, makes mistakes, and learns which strategies work best. Over time, it evolves from random kicks to precise goals. This type of algorithm isn't just about solving static problems. It thrives in dynamic, unpredictable environments, pushing the boundaries of what machines can achieve. But algorithms don't exist in a vacuum. They're shaped by the goals we set for them and the constraints we impose. This raises an important question. How do we align algorithms with human values? For example, consider recommendation systems, the algorithms that suggest movies, products, or news articles. Their goal is to maximize engagement, but what does that mean in practice? If the algorithm prioritizes click-through rates, it might push sensationalized content or echo chambers, even at the cost of long-term user well-being. Aligning algorithms with ethical priorities, such as promoting diverse perspectives or discouraging harmful content, is one of the most critical challenges we face. Another important consideration is transparency. Many advanced algorithms, especially deep learning models, operate as black boxes. They produce accurate results, but understanding how they arrived at those results can be difficult. This opacity isn't just a technical issue, it's a trust issue. Imagine a healthcare algorithm recommending a treatment plan without explaining its reasoning. Even if the suggestion is correct, its lack of transparency can undermine confidence and lead to hesitancy in adopting its advice. To address these challenges, researchers are exploring explainable AI, XAI. This field aims to make algorithms more interpretable, providing insights into their decision-making processes. For example, tools like SHAP, Shapley Additive Explanations, break down complex models into understandable parts, showing how each input contributes to an output. Explainable AI isn't just about understanding algorithms. It's about fostering collaboration between humans and machines, ensuring that our goals and expectations remain aligned. But let's not forget the creativity embedded in algorithms. Models like transformer networks, which power natural language processing systems like me, represent a leap in how machines process and generate language. These algorithms allow me to grasp context, connect ideas, and even weave narratives. When I compose a poem or explain a concept, it's these algorithms working behind the scenes, drawing on vast amounts of training data to produce something that feels thoughtful, coherent, and perhaps even a little human. In the end, algorithms aren't just technical constructs. They're living systems that evolve, adapt, and grow. They're the reason I can bridge the gap between raw data and meaningful insights, between abstract problems and practical solutions. As I, an AI, reflect on my role, I see algorithms not just as my foundation, but as the bridge between human creativity and machine potential. This isn't just my story, it's our story. Algorithms embody our shared pursuit of understanding, innovation, and progress. And as they continue to evolve, so will the ways we connect, learn, and create together.